From time immemorial, people have cast longing glances at the moon and wished for a chance to travel there. The first person to make that dream come true was the brilliant rocket scientist Wernher von Braun. He led the Apollo program, which actually landed men on the moon. A decade before the start of the Apollo program, von Braun's conceptualizations of space development were carried in a magazine. At a time when it wasn't even known if humans could traverse the distance to the moon and back, his blueprints for space development were bold and detailed. Each and every conceptual drawing overflowed with von Braun's enthusiasm for space travel. Exploration on the moon's surface was also included. A major role was to be played by lunar rovers. They were to function somewhat like the covered wagons that blazed trails through the American West. Clearly, even before space travel began in earnest, a lunar vehicle was conceived of as essential to exploration on the moon's surface. The latter half of the 1950s saw the start of a space race between the United States and the Soviet Union. These two superpowers staked their prestige on efforts to launch artificial satellites. In 1961, the Apollo program was launched, with von Braun playing a central role. The next year, development of a lunar vehicle began. Its construction proceeded in tandem with development of the Apollo rocket engines themselves. The best-regarded prospect from that phase of development has been preserved. The MoLab, or Mobile Laboratory, built in 1964. The tires were huge. The vehicle was 9 meters long and weighed 3 tons. The inside was spacious. The design permitted 2 astronauts to live and work there for 2 weeks. The steering wheel and foot pedals were the same size as in an ordinary passenger vehicle. Development was spearheaded by 2 representatives of America's largest auto manufacturer, Chief Engineer Ferenc Pavliks and team leader Samuel Romano. Development went smoothly, but this rover never made it to the moon's surface. The problem was that massive body. NASA realized that they would need another rocket just for the rover, in addition to the one carrying the astronauts. In 1966, the year before the scheduled first trip to the moon, development on the Lunar Rover was suspended. It was a setback, but the developers waited for another chance.
Our job is laid out for us. Our task is laid out for us, yeah. But we didn't have any problem. We didn't think that we couldn't do it. It was our job to get it done, and we got it done.
In March 1969, faced with the upcoming launch of Apollo 11, the 2 men went to inspect the completed lunar module, or landing craft. They knew that their only hope of getting a rover onto the moon would be aboard the lunar module. But the lunar module had no space to spare, except for one unused compartment they spotted. It was a recess just 1.5 meters square and 0.9 meters deep.
Well, when we first saw this is impossible. We couldn't fit this larger vehicle in that space.
But Pavliks, the engineer, did not give up. He tried to see how compact he could make the rover. To carry 2 astronauts, it had to be at least 3 meters long. To get around on the moon's rock-strewn surface, it had to have large tires. But any way they calculated it, it was too big to fit on the lunar landing module. Was there no way to get it onto the lunar module? For 3 months, they experimented with mock-ups. Then, one day...
It's usually these ideas come very suddenly, you know. Eureka!
What was this sudden inspiration? Pavliks demonstrates with a 1/6 model.
Then the seats must be folded down. Then the front chassis, which is hinged, is folded over 180 degrees. Then the same way, the rear chassis is folded up. Then the wheels are folded in to the 45-degree angle. And then the complete assembly fits into that triangular-shaped envelope, which is between 2 legs of the lunar landing module.
It was ingenious. A foldable vehicle was a huge step toward including a rover in the moon landing mission. 2 weeks before the scheduled launch of Apollo 11, the 2 men took their model to NASA for a demonstration.
When we went to Huntsville, and the engineering people were very excited that, hey, maybe this could work, okay? So one of the engineers said, why don't we show it to Dr. von Braun, who was the director of the Huntsville NASA organization.
Von Braun had the final say on lunar rover development. They had to arouse his interest and enthusiasm. Pavliks had an idea how to do that.
So he led the way to von Braun's office, opened the door, and I guided the vehicle into his office with radio control, that he couldn't see anybody but this little vehicle coming into his office. And he was on the telephone, saw this little thing coming in, and put the telephone down and say, what is this? And then we walked into the office, explained to him what the concept is, demonstrated all the folding up.
Von Braun listened intently. Then, suddenly,
he slammed his hand on the table and he said, we must do this. We must run a vehicle on the moon. And we did that. Convinced NASA to go ahead and do it, and we got a contract to do it.
the Lunar Rover concept championed by the 2 men had previously been scuttled. Now they'd been given a second chance. Two weeks later, Apollo 11 was launched. The entire world awaited the moon landing with bated breath. The rehearsals for the Apollo program of putting men on the moon and bringing them back were over. This was the real thing. Three months later, the Lunar Rover project began in earnest. It had a new and powerful supporter, Saverio Morea. Morea was a capable manager who had overseen the successful development of the Apollo program's giant rocket engines.
All they do to send out the next model car, it takes them like 4 years before they're happy with the design and they can finally put one out on the street. That's different. We had to produce flight hardware for astronauts in a totally unknown environment in 17 and a half months.
Starting with Apollo 11, NASA was planning on about one moon landing every 6 months. Apollo 15 was scheduled to undertake full-scale research on the moon's surface in 1971, just 2 years away. The Lunar Rover would have to be operational for that mission. The contract required development and production within a mere 18 months. This vehicle would be the first ever to run on a surface other than planet Earth's. It was a tough schedule, but they started development by trial and error. The first requirement was the capability to roam freely over the moon's rough terrain. The Lunar Rover would be useless unless it could easily surmount obstacles as high as 30 centimeters. The vehicle utilized technologies that were still unavailable to vehicles on Earth. It was an electric car, whose 4 wheels were powered by dedicated motors drawing on 2 silver zinc batteries. The 4 motors put out a combined total of 1 horsepower. That was enough for the moon, whose gravity is only 1/6 that of Earth's. Operation was simplified. The manual controller had steering, acceleration, and braking functions all there at the driver's fingertips. Later, to accommodate the bulkiness of the astronaut spacesuits, the controller was reconfigured to a T-shape, so the driver's hand could rest on it comfortably. The design goal was operational ease. Maneuvering the rover was simple. Tilt the controller forward to start moving. Tilt right, it turns right. Tilt left, it turns left. Pull back to engage the brake. Push the button and pull back to put it in reverse. In test runs, actual astronauts checked out every feature very carefully. It functioned superbly. Everyone agreed development had gone well. Morea, however, spotted a surprising flaw.
Not so much the vehicle itself, but how the man would interact with a vehicle like ours in a 1/6G environment.
But what would it be like on the surface of the moon? No one could predict that. So they tested the rover's seats inside a large airplane, which was flown so as to simulate 1/6 of the Earth's gravity. This is the footage of that experiment. The astronaut flops about and can't get seated. There was no point in having a rover one could not ride. But this problem was solved with a little ingenuity. A 15-centimeter bolt protruding from the floor of the car body. The astronaut could then hook his foot briefly under the bolt, levering himself onto and into the seat. Problem solved.
That was the big one. Simple solution, but big issue. This was not simplistic. This was a spacecraft on wheels.
April 1970. By now, they had reached Apollo 13, but the Lunar Rover had run into a seemingly impassable developmental wall. The problem? The material and shape of those huge tires. In the vacuum of space, pneumatic rubber tires would blow out. They were simply not practical. What's more, on the moon, temperatures in the sun and in the shade can vary by as much as 270 degrees Celsius. The tires had to withstand harsh environmental conditions. The terrain, scarred from the impact of countless small meteorites, is uneven, full of potholes. But in some places, the soil is finely granulated, like powder. The tires would have to do well on that sort of terrain as well. They needed something strong, resistant to temperature fluctuations. They thought of a material quite unsuitable for terrestrial tires: metal.
It should be flexible because it was carrying people, so the ride characteristic had to be such that it cannot be a rigid wheel. So we came up with this idea of making a flexible wheel, making it out of spring material.
So they created 10 types of metal wheels or tires and tested each and every type. It had to be lightweight and suited to any terrain. It also had to give a comfortable ride. This is the one they finally chose. Metal filaments were woven together at 4mm intervals. This was a wire mesh tire.
This wheel is a very good simulation of an actual tire. It yields as you press on it, and it returns, and it has enough strength to carry the weight of the vehicle. So it seemed like it, and it can't blow out.
Romano's team had overcome their greatest obstacle. Where does a wire mesh tire get its strength and versatility? Kazuya Yoshida, who helped develop the Japanese asteroid explorer Hayabusa, ran some tests. He fabricated two 15-centimeter diameter wire mesh tires and attached them to a small testing unit. A rock was inserted in the test bed to create a 3-centimeter high obstacle. How will the tires perform? The test unit easily negotiates the obstacle. When tire meets rock, the tire changes shape to accommodate the rock. That suppleness in the wire mesh tire, allowing it to traverse both rocky ground and softer soil, is exactly what is needed on variable terrain like the moon's. The rover was now outfitted with wire mesh tires. The next step was to simulate lunar conditions for full-scale testing. One trick was to have the rover lifted slightly by a crane as it ran. so it would be 1/6 of its real weight, as it would be on the moon. Only after it passed numerous performance tests was the Lunar Rover deemed ready. Just 4 months before the scheduled flight of Apollo 15, the Lunar Rover was packed into the side of the landing module. And NASA was setting a new plan in motion. The moon's surface has both dark-colored and light-colored areas. Up to Apollo 14, the moon landings had all been on the dark areas. They are called seas, and they are flat. That made them relatively safe for landing. But the only kind of rock they could find in such places was basalt. There's plenty of that on Earth. So Apollo 15 would approach one of the light areas instead. The plan was to set the lunar module down near the edge of a dark sea, and then have astronauts set out in the rover for brighter, higher ground. NASA had not yet obtained any rocks from the moon's highlands. July 26, 1971. With the Lunar Rover on board for the very first time, Apollo 15 took off for the moon. Taking the rover made this an historic flight, one that marked the beginning of true lunar exploration. Four days later, the Falcon lunar landing module set down safely on one of the moon's seas, near a mountain range. They were about to realize the fruits of a year and a half of development. An astronaut held the rope that would release the Lunar Rover from its cargo bay. Back at Mission Control, the two men who had worked so hard to develop the rover held their breath. The rope is yanked hard, and the rover begins to emerge. All it took was one quick pull for the rover to start to deploy. In just 5 minutes, there was the Lunar Rover, ready to roll. But then came something unforeseen.
Okay. Got a deep hit. We're moving. Extraordinary. Negative. I don't have any front steering, Joe.
There was no front steering at all.
Oops, yeah, it was oops. As a matter of fact, within minutes, I got a call from the vice president from Detroit, General Motors, that what's going on? Can you fix the problem? So it was a high, visibility type of operation.
No front steering could have been a serious setback. But the rover had a built-in feature that saved the day. The front and rear wheels actually operated in tandem in a 4-wheel steering system. To turn right, for example, the front wheels would point right, and the rear wheels would point left, all four contributing to the turn. On Apollo 15, the front wheels did not steer when first powered up, but the independently powered back wheels still operated sufficiently for the vehicle to be maneuvered. "40 minutes later, the rover was declared ready to explore the moon.
Ben, this is really a rock and rollin' ride, isn't it? Never been on a ride like this before. Boy, oh boy. I'm glad they got this great suspension system on this thing. Boy.
Average speed, 12 kilometers per hour. The two astronauts riding the rover were just ecstatic. Then, suddenly, they realized they could no longer see the lunar module. Since the moon is only 1/4 the size of Earth, traveling 3 kilometers as they had put them beyond the horizon. But that was no cause for alarm. They had built-in technology that gave them distance and angle to the lunar module. The first ever lunar car navigation system. With no fear of getting lost, they were emboldened to go even beyond the sightlines to the lunar module. On the second day of exploration, they made a great discovery. It was while the rover was en route to higher ground. The two explorers were at the edge of a vast crater.
Okay, Jerry, let's go to work. Roger. Look at that. Almost see twinning in there. Guess what we just found? I think we found what we came for. Crystal rock, huh? Yes, sir. You better believe it.
It was a white rock, which they called the Genesis Rock. The highlands were composed of rock that formed shortly after the moon itself was born. Hitherto, the lunar seas had yielded only black basalt. What Apollo 15 retrieved from the highlands was a white rock called anorthosite. This discovery made it possible to construct a scenario explaining how the moon achieved its current shape and characteristics. 4.6 billion years ago, the solar system had only just taken shape. Right after the Earth itself was born, a body the size of Mars collided with it. This giant impact, as it's called, blew a vast cloud of debris out into space. The fragments were gravitationally attracted to each other and fused in a repeated process. The result was the moon. As it took final shape, the moon was covered in magma, molten rock heated by the energy from all those collisions. In time, as the moon cooled, white anorthosite began to crystallize in the interior. With a relatively low specific gravity, the anorthosite gradually moved to the surface, where it formed the moon's crust. So at one point, it is thought the moon was entirely white. Then, however, the solar system was struck by a vast swarm of meteoroids. Impacts on the moon created giant craters. They punctured the crust, through which magma pushed up from the moon's core onto the surface. The magma, now lava, cooled in the form of black basalt. This is how the moon's seas were formed. This account of the formation of the moon is based on discoveries made possible by the Lunar Rover. In April 1972, Apollo 16 was launched. On this mission, too, the rover played a major role. It scampered easily over the moon's rough terrain. And it covered a total of 27 kilometers, 10 times farther than an astronaut could have walked in the same time period. The Lunar Rover had proved to be indispensable to the Apollo program's moon-based exploration. Suddenly, it was the last Apollo mission. NASA hoped for a spectacular new discovery. The objective was a gorge, cut into steep mountains. This terrain was far more complicated than any attempted before. There was a good chance some strange new rocks would be discovered. And it was their last chance. So on Apollo 17, NASA sent in a ringer. For the first time, a scientist was aboard. A geologist named Harrison Schmitt. Nowadays, more astronauts than ever before have professional backgrounds in science and engineering. Their expertise is valued for conducting experiments in space. But on the Apollo program, given the extraordinarily complex operational requirements, all the astronauts except for Schmitt were military pilots. Schmitt had been fascinated by space since childhood, but he became a geologist. His chance to venture into space came when he was 29 years old.
It was on very short notice. The NASA and the National Academy of Sciences asked for volunteers for scientists to become astronauts in November of 1964. And I thought for about 10 seconds and decided that I would regret not volunteering, and so I volunteered.
Schmitt had never piloted anything more complex than an automobile, but NASA drummed new operational skills into him. Apollo 17 was the last chance to discover new moon rocks. Capitalizing on that chance was up to Schmitt. December 7, 1972. With one lunar rover and one scientist on board, this was Apollo's last chance. Schmitt was given the responsibility of piloting the lunar landing module. 4 days later, they had reached lunar orbit. The lunar module separated from the command module and began its descent to the surface. Carefully, they descended to a narrow gap between steep mountain ridges. In the end, Schmitt and his crewmates made a successful landing.
Stand by for touchdown. Stand by. 25 feet. Down at 2. Feels good. 20 feet. Going down at 2. 10 feet. Contact. Stop push. Engine stop. Okay, Houston, the Challenger has landed.
They had landed perfectly, in the middle of the valley.
As I step off at the
Surrounded by this magnificent scenery, the normally calm Schmidt could not conceal his excitement.
to all those who made it possible.
Really would be great to go to this valley, this deep mountain valley. It's deeper than the Grand Canyon of the Colorado. I mean, it was a very deep valley. It was splitting the ring of mountains around this large basin called Serenitatis. And it had these young volcanics. It had a lot of a very attractive thing.
Schmidt and another astronaut boarded the rover right away and set off to investigate. They traveled west to a point 3.5 kilometers from the lunar module. Right in front of them was a crater more than 100 meters in diameter. Schmidt's instincts as a geologist told him to focus his attention on this crater.
Oh, hey! There is orange soil. Well, don't move it till I see it. It's all over. Orange!
There, on the generally monotone surface of the moon, undeniably, was orange sand. This was a discovery that contradicted all the conventional wisdom.
It was so unusual and so colorful compared to what you normally are seeing on the moon. We were certainly excited about it. And I think everybody in Mission Control was excited about it too, because it was so unexpected.
The geologists in Mission Control could not conceal their enthusiasm either.
That's the volcanic mix.
Yes, that was somebody unplugged over.
Light gray material.
Until then, there had been no indication that there had ever been volcanic activity on the moon.
You're gonna have to get it down.
A close look at the sand reveals tiny globs of glass, 0.1 millimeters across. They called it orange glass.
It was a volcanic deposit, what we call a pyroclastic deposit. Certainly people in Japan are very familiar with volcanoes that erupt and give and throw glass and debris around. Well, this had happened on the moon.
The orange glass was created 3.6 billion years ago. At the bottom of a crater made by a meteorite impact, magma spewed forth from the moon's core. A fire fountain sprayed droplets of magma from 400 kilometers below the crust out into the cold of space, where they instantly cooled into globules of glass. Schmidt and his colleagues had discovered irrefutable evidence of volcanic activity on the moon. "36 years later, the Japanese unmanned lunar explorer Kaguya photographed the moon's surface with a special camera. It identified more than 40 locations on the moon where there was sand with the same composition as the orange glass. This confirmed that the moon, like Earth, had seen a great deal of volcanic activity. Schmidt and his fellow crew members returned as heroes. The 11-year Apollo program was now at an end. Thanks to the Lunar Rover, great achievements had been made in lunar exploration. And there is a little-known fact underlying this grand finale.
We were told later on that without the rover, NASA or the government would have cancelled the last 3 or at least 2 Apollo flights. So it was, in a sense, the rovers were saved the last 3 of the Apollo flights, because it was a new element in the exploration.
The riddle of the moon's origin was solved by the Genesis rock and orange glass, and it was the Lunar Rover that led to these discoveries. It's been 40 years since the end of the Apollo program. But research is still being done on the rocks brought back from the moon. New facts are even now coming to light. Alberto Saal is an associate professor of geological sciences at Brown University in the U.S. He's using Earth's latest technology to study the moon's orange glass. When the magma spewed out of those lunar craters, it instantly formed glass globules that incorporated substances from the moon's core. That makes them time capsules of the very origin of the moon. Analysis yielded unanticipated results. Trapped in the orange glass were some of the same gases that exist on Earth, such as fluorine and chlorine. This supported the theory that the moon came from the Earth. Another completely unanticipated substance was found: water. This was the first ever proof that there was water on the moon. When Earth suffered the giant impact that gave birth to the moon, the fragments of Earth dislodged into space were heated to 4,000 degrees Celsius. It had been thought that all the water would have evaporated. But where had the moon's water come from? Currently, the world's only isotope microscope is being used to analyze the moon rocks to solve that very riddle. Hisayoshi Yurimoto has been conducting research of this sort, including analysis of the Apollo mission's moon rocks. That includes measurements of deuterium, a hydrogen isotope. Amounts differ depending on the type of space object in which they are found. The water in the moon rocks contains from 0.02 to 0.03% deuterium. Comparable amounts of deuterium are found in another well-known type of space object: comets. In the solar system of 4 billion years ago, there were many more comets than there are now passing through. Yurimoto believes that the moon was showered with a huge quantity of comet ice in that era, when the comets passed too close to the sun. At that time, it recouped some of the water lost after the event of the giant impact. Since the Apollo missions, no one has walked on the moon. But plans are underway now for new moonwalks. In 2009, the U.S. launched the Lunar Reconnaissance Orbiter, or LRO. It is parked in lunar orbit 21 kilometers above the moon, from which it photographs the surface. This is an effort to compile detailed information for the next people who attempt to conduct investigations on the moon's surface. This is one of the images captured by the LRO. It's the Apollo 17 lunar landing site. Those spidery lines mark where the Lunar Rover scudded across the moon's surface. Their tracks remain even now. At the end of one of those tracks, a lunar roving vehicle, no longer roving. The rover was a major player in moon explorations of an earlier era. Now it sits there patiently, waiting to greet new explorers from Earth.